Another kind of series that's really helpful, not as much as geometric series, but more than most other series, is the telescoping series. So again, it's a type of series, so it's not just one of them, but there are several. And the telescoping series is a series that whenever you try to add the sequence of partial sums, let's say I try and do Sn, I do SA1 plus A2 plus A3 plus A4 and so on, up until AN maybe, because that's not an infinite sum yet. That's finite sum, the sequence of partial sums, so it ends at AN. Whenever I try and do that, it could happen that when I add A2, nothing happens, but then when I add A3, maybe it cancels. And then when I add A4, maybe nothing happens, but then next time it cancels, and maybe everything else cancels. It seems like it's a super large sum, but because everything cancels, it sort of collapses down to just a few terms. Now, that's not a general formula. Sometimes you need more terms than this, but because there's a big sum that collapses into a small sum, just like those sort of stereotypical pirate spyglasses that sort of collapse for you to store them in a pocket somewhere, then you call those telescoping series. There's like a famous scene that I remember at least from Pirates of the Caribbean with Jack Sparrow sort of bringing a spyglass from the pocket of multiple pirates in a row, and Jack is the last one. And then extending the telescoping the spyglass, and a telescoping series will do the opposite. It looks super large, but you can collapse into something smaller that is more agreeable for you to calculate. Now, a general tell for this is not a hard rule. Again, it's just a general idea. Whenever you see a fraction with a denominator that seems factorable, something that can factor, usually by a partial fraction decomposition, then I will think that maybe this is telescoping, and then I will proceed this way. So there isn't much to talk about in terms of theory here, other than doing an example and hoping that you can understand how this comes from. So if you look at this term, I'll just look at an right here. An is 1 over n squared plus n, and I can see without a sum, right? An is just a number for each n, just the sequence. And I can factor its denominator as n times n plus 1. And I remember from Calculus 2 learning how to integrate those things using partial fraction decompositions. And so I know I can decompose this like this. And so whenever I think this way, I think maybe this is telescoping. So I'm going to see what's going to happen here. Let's find a and b, and generally my way of finding a and b is taking this last equation, multiplying both sides by n times n plus 1. So when I multiply the left side, the denominators cancel, and then I get 1 on the left. When I multiply the right side, I have to use distributive property. So I multiply this times the first term. When I do that, the n's cancel, and I just get a times n plus 1. And when I do that, the n plus 1's cancel, and I just get b times n. And so I do that because now I'm free to plug in certain values of n. So when I plug in n equals 0, this whole b goes away, and I get that a equals 1. And when I plug in n equals negative 1, this whole n plus 1 goes away, so a goes away, and then I get that b equals negative 1. So that means I can rewrite my an as 1 over n minus 1 over n plus 1. And this negative here is another possible tell. Whenever I do my partial fraction decomposition, I don't see a negative somewhere, so negatives and positives somewhere, then I get a little concerned. Okay, so this is the new an that I'll use. It's equal to the previous an, so I was doing this. And that equals this. So if one converges, the other converges. If one diverges, the other diverges. So what am I going to do here? I'm going to calculate the sequence of partial sums manually. So this is why this is less agreeable than geometric series, but still it is something that you can do. So it's S1. Well, that's just A1. So I plug in 1 here. So A1, you can plug in whatever you'd like. You can do 1. When n equals 1 minus 1/2. Of course, this equals 1/2. If you do this, you can see. But I'm not going to plug this in. I don't want to expand this. I want, I don't want to combine it now. I want to keep it that way to see if it maybe cancels out in the future. So what will S2 be? S2 is A1 plus A2. A1 I've already calculated, so I'll just repeat it. But now I got to do A2. I go here, plug in 2. So that's 1/2 positive minus, go here, plug in 3. Plug in 2, I get 1/3. So you see exactly what I was saying happened? The 1/2s in the middle canceled. So even though it looked like a large sum, this is 1 minus 1/3. S3, A1 plus A2 plus A3. So if I were to write the entire thing, that would be 1 minus 1/2. I'm not going to write it all. I'm just going to write the 1 minus a third that I've already canceled, that I've already calculated before. So these two. This is 1 minus 1/3. This is S2, right? And then the next term is me plugging in 3. So I go here, plug in 3. That is plus 1/3 minus 1/4. And again, these cancel in the middle, and I get 1/4. 1 minus 1/4. So you can continue until you see, or until you convince yourself that Sn equals, for any n, 1 minus 1 over n. And that is great, because now you can take a limit when n goes to infinity. And this is not a hard limit to find. Sometimes those will become a little harder. As n goes to infinity, this goes to 0, so this is 1. Okay? And so the sum of 1 n squared plus n from n equals 1 to infinity equals 1. Yes? If I wanted to, I could have done a little more. I could have said, and I'll let you think about this. Can you find this sum? Or maybe starting at a later value. Like this. Using properties of series and what we've just talked about, you can do this. But I'd like to think about that yourself.